Hey guys, welcome back. This is going to be the fourth and final part of the circuit notes, the physics circuit notes. I'm going to go over a couple components and do the last problems that's going to talk about power. So how energy is used up in a circuit. In our circuits, we're going to use LEDs, which are light emitting diodes. And this is not a resistor like you could consider a simple light bulb. The idea of an LED is that it tells us that a circuit is working. So if you think about right now, the camera's on and there's a green light on. That green light on my computer is there to tell me that the camera's on. And that's what we're going to use our LEDs for, is to show us that we have a complete circuit. When you're looking at an LED, you want to look top down at it. You don't want to look sideways at it. They're designed so that you're looking top down. If you think about how it is like on the front of a television or the front of a computer, you're always looking straight down at the LED. There's a positive and a negative side to an LED. The positive side is always longer. And that's the case for other components that have positive and negative sides. LEDs work by electroluminescence, which you don't need to worry about, but it's a controlled drop. And so we don't lose any energy to heat in these situations. So we have an electron that is changing energy levels very specifically, and it gives off a specific amount of energy from that drop. The symbol for an LED is an arrow going this way. If it's by itself, it's just a diode. These little lines here represent light. So they're supposed to represent photons. We also have wires. For us, the symbol for a wire is just going to be a straight line. For our battery clips, and this is something that's good for the rest of your lives to remember, that black is negative and red is positive in electronics. And again, we're going to say that the longer line is going to represent the positive side of the battery. We are going to use breadboards. They're called breadboards because they look like pieces of bread. If you think about a close-up look of a piece of bread, it has little holes in it. The idea of this is so you don't have to hold wires together or solder wires together. So inside of each one of these little holes is two pieces of metal and that are spring together. So if you put a wire in, it'll hold that wire in that one spot. On these breadboards, all of these are connected to each other. All 5 of these across there. On the edges, these are all connected to each other. So the idea is that you could put something in this one and then put something else in that one. And since they're connected underneath here, we can't see. I've now connected these 2 wires. And so now I have one there. I can put one in the same row. And now these 2 wires are connected. I could put one in the same row. And now those 2 wires are connected. And so you can connect components like that. Now, the row does not continue across the middle part. So this break here does not continue it apart. In our labs, the switch is going to stay just in one single spot. So you don't have to ever take it out. It has like tricky legs on it. You're going to have a variable resistor. It has a dial on it. Look close to this picture, not exactly. And the idea is that you're going to use this leg and then this one or that one. So you don't use both of them. So one or the other. And by twisting it, you're going to get different resistances. The schematic symbol for a variable resistor is the schematic symbol for a resistor with an arrow diagonally going through it. So that tells me that it is variable. All right, last equation, which is going to be power. So And again, we want to connect everything to energy, right? Like that's the one thing that is going to bring all of physics together. When I told you guys on the first day of school, if someone asked me, what is physics? I would say it's the study of energy. So that's the most basic thing you can break it down to, is that it's the study of energy. The power that is dissipated, so the power that is used up in a circuit, is going to be equal to the product of the current times the voltage. P is equal to IV. It also ends up being equal to I squared R. This is going to be in watts. That should be a capital W. I'm not sure why it was lowercase w. This is the same as it was in Newtonian mechanics when we calculated power. Current is going to be in amperes. Resistance is going to be in ohms. Our voltage or our potential or our EMF is going to be in volts. All right, so how much power is dissipated in a 1,000 ohm resistor that is attached to a 9-volt battery? So you're going to assume you have ideal conductors, so we can apply the equation derived from Ohm's law. We know that P is equal to IV or equal to I squared R, but we don't have I, but we know V and we know R, and we know that our current is going to be equal to our voltage divided by our resistance. And so this is going to be equal to 0.009 amperes. And so my power would be equal to 0.009 amperes times 9 volts, or 0.081 watts. Or this should also get us 0.081 watts. Yeah, they're going to be the same. All right, so this alternating current that we receive in our homes goes from 150 volts to negative 150 volts, and it averages out to about 120 volts or 115 volts on average when we take what this average out to. These cycles, one of these cycles, the time that this would be 1/60th of a second for one of them. So we're saying it happens 60 times every second. It's going from 150 to negative 150. Different countries have different outlets because the voltage isn't the same. So here are some pictures of ones. You can see North America is pretty consistent. I think that I like this one the best. I wish ours looked like that. Like this guy looks happy. Ours kind of just looks concerned. All right, a light bulb is rated at 40 watts. What is its internal resistance? So the thing that's constant in the light bulb is its resistance. It'll be as bright as whatever you plug it into. Typically, we just plug things into 120 volts. So that's what we get when we plug things in. I'm going to say that V is equal to IR. I also know that P is equal to IV. So my current is going to be my voltage over my power. So this is going to be 120 volts over 40 watts, or 3 amperes. And then my resistance is going to be 120 volts over I flipped this. I saw it right away. I'm like, what am I doing? I'm not getting the right thing. All right, sorry about that. So my current is going to be P over V, not V over P. This is telling me that I should take a break from making these because do something else and come back to it. That's what it's telling me. So I have 0.33 amperes, and now I can say that R is going to be V over I, which is 120 volts over 0.33 amperes, or 360 ohms. So energy consumption in our homes, certain things use up more joules per second than other things. You think about like an air conditioner or a pump for a pool or a dehumidifier. All of those are going to use up a lot of energy. Light bulbs typically don't use up a lot, but the newer compact fluorescents or LED ones, you get the same brightness for an eighth of the energy, a fifth of the energy, depending on what it is. We're charged for energy. So if you get an electric bill, it comes in kilowatt hours. And this comes from energy being equal to power times time, right? Because we said that power was work over time or energy over time. So 1 kilowatt hour, 1 hour is 3,600 seconds. And so, and then 1 kilowatt is 1,000 watts. So 3,600 seconds times 1,000 watts gives us 3.6 times 10 to the 6 joules. And typically your electric bill would be like 10 kilowatt hours, 20 kilowatt hours. They don't use joules because you could see how it would cause some confusion if people were getting a bill for millions of joules or tens of millions of joules, right? So if it's 10, it's, 36 million joules. If it's 20, it's 72 million joules. So that's why we use kilowatt hours. All right, the power company charge, I'd probably update this too, I'm sure they charge a lot more. 11.5 cents per kilowatt hour. How much would it cost Molly to dry her hair for an hour if the power rating of a hair dryer is 2,500 watts? So I want to convert this to kilowatts. So this would be 2.5 kilowatts. And so to find out how much it would be, I would have 2.5 kilowatt hours, because we're saying it's 1 hour, multiplied by 0.115, so 11.5 cents per 1 kilowatt hour. And so this is going to cost us $0.2875. So they would charge us 29 cents because they always round up. And they really get you more on fees than what the electricity costs. That's the big cost in this.